Good morning, everyone. Today we are going to start what's called rate laws. And this is actually a long lecture. I'm guessing I'm going to have to break it into two. So I'm just going to keep track of how long the lecture's going. And then once we get to a certain point, we'll just stop and we'll start again on another day. Last class we started to talk about reaction rates and calculating instantaneous rates and calculating average rates, and we're going to expand on that a little bit. So, as we've said before, we know a chemical reaction occurs as a result of molecular collisions. So we know that for a reaction to happen, we got to have two things that collide, and when they collide, they have the chance of reacting. It doesn't mean they're going to, all right? But it really has got to do with those number of collisions. So that means the larger the concentration of reactants, the greater the number of collisions in a given time. Okay, so if we have a lot of stuff, there's going to be more collisions, and then if there are more collisions, okay, there's going to be a faster reaction rate. Now, usually, not always, but usually, as a reaction progresses, so from the time that we start till the time that we end, the reaction rate slows down. So, for example, let's say we have a general reaction A plus B going to AB. At the very beginning of the reaction, the concentration of A and the concentration of B are really high. There's lots of reactant. Okay, which means when the reactions start, there's going to be lots of collisions. As the reaction progresses, though, the concentration of A and the concentration of B are going to go down. Okay, if the concentration of these go down, the number of collisions is going to go down. So over the reaction lifespan, the reaction rate is going to decrease. Okay. So over time, the concentration of our reactants decreases, which means our reaction rate will decrease. So that means there's a relationship between reaction rate and concentration. Okay. And that brings us to what's called the rate law. And we'll start, and then I'll switch pages. That brings us to the rate law. And the rate law is the relationship between reaction rate and the concentration of the reactants. So let's look at an equation. So let's say that we have 2 N2O5 gas going to 4 NO2 gas and H2O gas. Well, we know we can actually write how to calculate the reaction rate in terms of reactants or products. Okay, so the reaction rate in terms of reactants would equal negative delta change in concentration of N2O5 over 2 delta T. Okay, so this is what we were talking about last class. Okay, so this is our reaction rate in terms of our reactants. Now, the rate of a reaction is usually found to be proportional to the reactant concentration. Raised to some power m. Okay, so we can rewrite our reaction rate ends up being equaling K times the concentration of N2O5 to some power m. And I want to talk about this. So K, and this is a lowercase k, K is called the rate constant. The m, or this order, is the order of the chemical reaction with respect to the reactant, which in this case is N2O5. Hang tight, because this will hopefully come clear in a few minutes. So, something to remember, and this is a big mistake that students will often make when we're dealing with the rate law. So let's start this. Never assume m to be the stoichiometric coefficient of the balanced equation. Okay. So when you write the equation, this don't get confused, okay, and don't automatically assume that m is going to be same as this coefficient up front here. Okay, sometimes it is, okay, but it doesn't have to be. All right, so when we're trying to figure out m, there's a way that we're going to figure it out. All right, so just don't assume that it's this coefficient. So let's talk about a little bit about what m means for these different orders. So how do we find this M? Okay, so let's write this again. Reaction rate is equal to our constant times the concentration of N2O5 to the M. Okay, so we're going to focus on this M right now. So how do we find M? So M is found only from laboratory experiments. And I'm going to star this also. There is no way to theoretically predict the M, or order, of a reaction. So the only way we can figure out M is by actually doing the reaction and taking some times and concentrations and things. You can't just calculate it somehow, right? You need lab data. Laboratory experiments. All right. So now, if we calculate these M's, what do they mean? Well, let's say that if M is equal to 0, we say this is a 0 order reaction with respect to the reactant. Okay. Sometimes we'll say that it's zeroth order. Now, if a reaction turns out to be a 0 order, what that really means is that the reaction rate is independent to D of the concentration of the reactants. In other words, changing the concentration does not change the reaction rate. If this is the case, if it's 0 order, the reactant does not show up in the rate law. Okay? It doesn't show up in the rate law, and here's why. All right, let's say that we have N2O5 to the 0 order. Okay, well, what does this mean mathematically? Well, if anything's to the 0 order is equal to 1. Okay, so if this is to the 0 order, that means this whole thing is just going to be 1. And what's 1 times anything? Anything. All right. So yeah. All right. Now, we've actually seen a 0 order process. Radioactive decay is actually 0 order. The reaction rate doesn't depend, or that decay rate does not depend on how much of the substance we have. Half-life is a constant. So if we have a ton of material, the half-life is still the same as if we have a small amount of material. Right? So we've actually seen one of these zero-order processes already. All right, so this is if the order equals 0. Well, what if the order equals 1? Which is also considered to be first order. So this is first order with respect to reactants. So in this case, our exponent, okay, so this would be K N2O5 to the first. Okay, our exponent would be 1. So if we have a first order reaction, what this tells us is that it's a direct relationship between concentration change and the reaction rate. Okay, so this is a direct relationship between concentration change of the reactant and the reaction rate. Okay, what does that mean? Okay, what does that mean? Well, if concentration is doubled, that means our reaction rate will double. Or if concentration is, I don't know, halved, our reaction rate will halve. All right. Well, what if we have m equal to 2, or second order with respect to reactants? Okay, so our exponent would be 2. If it's second order, remember this is a relationship between concentration and our reaction rate. So in this case, when we have a second order reaction, if concentration is doubled, the reaction rate will increase by a factor of 4. Okay. So if it's doubled, okay, we're going to quadruple the rate. Okay, so this is the relationship if m equals 2. Now, before we actually get into calculating some math, I kind of just want to put some terms down, and just so they're all next to each other, because we got reaction rates, we got rate laws, and we have a rate constant. So there's a lot of similar things here. All right, so before we actually put this all together and start doing some calculations, I just kind of want to summarize. So let's start with reaction rate. Okay, so when we're talking about just the reaction rate, we're actually talking about the speed the reaction is taking place. And remember that speed can change. Okay, it's like, okay, it can change as the reaction's happening. So it's an instantaneous point in the reaction. How fast is it going? All right, so this varies or changes with concentration and time. And our units for reaction rate are always moles per liter dot seconds. Or you could write it moles dot liter to the -1 dot second to the -1. Same thing. Okay, so this is our reaction rate. Now, what is rate law? So the rate law is the mathematical relationship between the reactant concentration and reaction rate. So in our rate law, our reaction rate is going to equal to some constant K times the concentration of one of the reactants to an order, and let's say M. If we have another reactant, that would also be included. So maybe we have reactant B, and that would be to the N or some order. And then if we have another reactant, let's say C, that would be, a lot of times we'll use Z. Now, we don't very often have more than two reactants. Okay, there's not a lot of reactions that actually have three reactants, and very few that have four. All right, because remember, for a reaction to occur, if there are four reactants, all four of those molecules would have to collide all at once for the reaction to happen. So 3 is rare, 4 is even almost non-existent. All right, so most of the time we're only going to have, in our rate law, we're only going to have 2 reactants at the most, but you could have a third. All right, so this is our rate law. And then finally we have the rate constant. All right, and that's our K. Okay, so that's this K right here. So our rate constant is a constant value at a fixed temperature for any given reaction. So the K is going to change depending on the type of reaction that we have. So the Ks are always different for every type of reaction. And they will change depending on temperature. Okay. Now, got to be careful with units for these constants. So our units depend on the orders, or the order of the reaction. So these units are going to change. So you're going to have to be really careful with units. And we'll talk a lot about units. All right. So in reality, the rate law incorporates both the reaction rate and our constant K and the concentration of our reactants. All right. So this rate law is kind of like the summary of all of this, and we have to be able to write this rate law, and then we can use that rate law to calculate rates of the reactions. All right, so that's just kind of a summary of some things that we're dealing with here. So let's actually try some calculations and actually look at what we have to do here. All right, so let's stick with that same reaction that we've been talking about. 2 N2O5 gas going to 4 NO2 gas plus O2 gas. Now remember, when we're trying to figure out the rate law or those orders, you can't theoretically do it. You have to have data of some sort. All right, so we have to do this in lab and take some measurements. So let's say that we go in the lab and we take some measurements and we get some data. So we do an experiment and we collect the following. So I'm going to give you a data table. All right, so we're going to have the concentration of N2O5 in moles per liter. And we have the reaction rate in moles per liter seconds. All right, so at 0.10 we have 0.085, at 0.20, 0.34, 0.30, 0.76, and 0.40, 1.4. All right. So the first problem of this is we're going to calculate the rate law. So A would be derive the rate law. So we start with reaction rate equals some constant K, and in this case we only have one reactant, so it's the concentration of N2O5 to some order M. Okay. We need to calculate M, right? That's part of the rate law. We need to know the order. So what we're going to do is we're going to use our data up here. So to calculate M, we're going to use the first two concentrations. So for my first rate, okay, so our first data set, rate 1 is equal to K times the concentration of N2O5 to Rm. Okay, so the rate is 0.085 equals K. We know the concentration is 0.10 to the M. So we can fill that in for our first data set. Now let's talk about our second data set. And we're going to do the same thing. Rate 2 is equal to some constant K times N2O5 to the M. Well, our rate 2 is 0.34 equals some constant K times the concentration of nope, we know the concentration is 0.20 to some order M. So now we do some fancy math, and it's really not fancy math. What we're going to do is we're going to divide equation 2 by equation 1. And when you do that, you must get a number greater than 1. All right, so let's go ahead and do it. So we're going to take equation 2 and divide it by equation 1. So we're going to take 0.34 equals K times the concentration of 0.20 to the M, and we're going to divide that by our first equation, or 0.085 K to the 0.10 M. All right, so now we can actually do some fancy dancy work. Okay, so the K is the same on top and bottom over here, so those just cancel out. So that's kind of nice. All right. When we do this division, we get 4.0. When we do this math, we end up with 2.0 to the M. M ends up being 2, which means this is a second order reaction. With respect to N2O5. All right, so now that we have this, we can write the rate law. Our reaction rate is equal to K times the concentration of N2O5 to the second. Okay, so this right here is our rate law. Now that we have the rate law, there are other things that we can play with. Okay, so there's a B part of this.